In the last few lectures, we had been looking at dimension reduction techniques. These were primarily the principal component method and the factor analysis method. There is a third way in which we can summarize the results, and that is referred to as the canonical correlation analysis. In today's lecture and in the subsequent lecture, we would be discussing canonical correlation analysis. Today we will be looking at what canonical correlations are, what canonical variables are in fact, and canonical correlation coefficients are, what do they stand for, how do you calculate this, and what their interpretations are going to be like. In the subsequent lecture, we will be looking at some of the results related to canonical variables and canonical correlation. We will now be looking at canonical correlations. What does canonical correlations do? Canonical correlations seek to identify and quantify relationship between two sets of variables. What do we mean by that? Remember that when we look at correlation, it has to be between two variables, x and y. That was a simple correlation that we started with in statistics. Now, later on what we did was we shifted to the multiple correlation. What was the multiple correlation? It was a correlation between a set of variables x1, x2, xp with another variable y, and in the regression model we called y as the dependent variable. But what we were trying to see was that how this set of variables are related together. So, in this case we have a set of variables and another variable, and when we do that regression, obviously we take the linear combination of the given set of x variables. Now, let us go a little further. Suppose we have two sets of variables now. It is not a single y, but there is another set of variables, and we want to find out the relationship between these two sets of variables all taken together. We do not want individual relationships. That means we do not want the relationship between one variable from this set, another variable from that set. We want to see the impact on the whole set of the other variables. That is what canonical correlation would do. And we will later on see, as you can well understand right away, that multiple correlations or simple correlations would come out as special cases of canonical correlations. Do look at two sets of variables, and as I said at the very onset, you can only calculate correlations between two variables. You need to reduce the set into two variables. And how do you reduce each of these sets to a single variable? You take a linear combination. So, if I have set 1 and set 2, then I take a linear combination of the variables of set 1, and I take another linear combination of the variables of set 2. And then I look at the relationship between these two linear combinations. That is what basically the canonical correlation analysis does. The combinations that we take leads to what are referred to as canonical variables. One canonical variable for the first set, another canonical variable for the second set, which are primarily the linear combinations of the original variables. And now we find the correlation between these two canonical variables, and we call this the canonical correlations. So, that is what canonical correlation is in a nutshell, but the problem is how do you take the linear combination? Which linear combination? Because there can be several ways that you can combine each of the two sets of variables. So, we need to find some ways of doing it so that there are certain criteria we can fulfill. That would be the basic problem in canonical correlation analysis. To look at that, let us start by defining certain variables. Put this mathematically. Now, suppose we have two groups of variables, the first group having R variables, and we put them in the random vector x1. The second group has S variables and we put them in a random vector x2. So we have a R by one dimensional vector and we have a R S by one dimensional vector, and we want to find the correlation between these two sets. As we shall see later on, let's for simplicity assume that R is less than equal to S. It could be the other way around, but one of the sets would obviously be either having smaller number of variables, or both the sets may be having an equal number of variables. So for the time being, assume that the first set has a smaller number of variables. Now if you look at the random vectors, assume that expectation of x1 is equal to mu1 with a covariance matrix equal to sigma 1 1. Similarly, assume that expectation of x2 is equal to mu2 with a covariance matrix of sigma 2 2. Finally, assume that the covariance between the first set and the second set is sigma 1 2 or sigma 2 1 prime. It's a symmetric, it will be symmetric in this sense. Now what we do is we put the two sets into a single largest set of m variables. So m is equal to r plus s, and we have x, which is a m dimensional vector, as x1 and x2. So the first r of the elements of x are from the first set, and the last s of the elements are from the second set. So x is x1 x2. Now given what we have defined before, the mean of x would be mu, which is mu1 and mu2. Again, it's a r plus s dimensional vector with the first set coming from the first group and the second set of s elements coming from the second group mean. The covariance matrix can be written as sigma, which is basically block matrices composed of sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. The two diagonal blocks are the variance covariances of the respective variables x1 and x2, and the off diagonal elements are the correlations between this. Now let us spare a little time on what sigma 1 2 is. Sigma 1 2 are elements, has elements which come from the correlations between one first group variable and one second group variable. How many elements do you have in sigma 1 2? There are rs elements, r from the first group with the s elements from the second group. Now you can see that if we want to find the relationship between the two groups, we can talk in terms of this rs correlations. But obviously these rs correlations are not too easy to get information from. So if you just read out these rs correlations, it will not make any sense. It will give you very informative idea of how the first set variables are related to the second set, but it will not be comprehensible. So we need to synthesize this, and that's basically what our purpose is. So instead of looking at this rs correlations between the first set variables and the second set variable, we want to do this in maybe 1, 2, 3 correlations, which would actually collect all this information and give us much more concise results so that it can be interpreted. How to do this? Let's begin by assuming that we take a linear combination of x through a coefficient vector a. So we have u is equal to a prime x1. Mind you, u is a scalar. So x is a vector, a is a coefficient vector, and a prime x gives us a scalar, which is a linear combination of the x's elements in the first set. Similarly, we define v as a linear combination of the elements in the second set, and v is given by v equal to b prime x2. And the intention is to find the correlation between these two variables u and v. That will give us a single correlation which would be reflecting the two sets. Now from standard results, we have variance of u is equal to a prime covariance of x1 a, which is a prime sigma 1 1 a. Variance of v is b prime x2 b, which is b prime sigma 2 2 b, And the covariance between U and B is A prime covariance x1 x2 into B, which is A prime sigma 1 to B. And the correlation between U and B is therefore given by A prime sigma 1 to B divided by the square root of A prime sigma 1 1 A into B prime sigma 2 to B. Now, the question is, what should be our choice of A and B? We define it this way. The first pair of canonical variables, that means the first pair of U and V, is such that it maximizes the correlation between U and V. So, we will choose A and B in a manner which would actually maximize correlation U V. Once having done that, we can go to another choice. That would be the second pair of canonical variables. And how do you get the second pair? It will again maximize the correlation between U and V, but now these combinations would be orthogonal to the previous combinations. This is exactly the same way that we had been looking at the principal components. So, we will be choosing these combinations in an orthogonal fashion. The first one will be maximizing the correlation between the two sets. The second one would be the next highest correlation between the two sets, and the combinations would be orthogonal to the first one. The third highest correlation that we can achieve, and in that case the combination would be orthogonal to both the first and the second. This way we can proceed up to the rth canonical correlation. Mind you, R is less than equal to S, therefore, we can only go up to R of this. To summarize these results, and we can show this as a proof, if we do a little bit of mathematics here, what we can show is that, to summarize the results, what we can now show is that the first canonical correlation is given by square root of lambda 1. I will come and explain what lambda 1 is, and the corresponding canonical variables would be U1, which is P1 prime sigma 1 1 to the power minus half x1, and V1, which is Q1 prime sigma 2 2 to the power minus half x2. So, what are this lambda P1 and P2? The remaining sigma 1 1 and sigma 2 2 are known to us already. Now, what will be this lambda 1, P1 and Q1? Consider the matrix sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 to the power minus half, sigma 2 1 and sigma 1 1 to the power minus half. This is a R by R matrix, and we can find the eigen values of this. This would be given by lambda 1, lambda 2, lambda R. And suppose we order this eigen values such that lambda 1 is the largest of them, next we have lambda 2, and then it decreases to lambda r, which is the smallest. So, lambda 1 basically gives us the first canonical correlation. This is the largest eigenvalue from the given matrix which we have just described. And what are P1, Q1? First of all, P1. P1 is the eigenvector corresponding to this eigenvalue lambda 1 obtained from the given matrix. So, as we did for the principal components etc., we have a eigenvalue eigenvector pair, and the eigenvalue actually the square root of that gives us the correlation, and the eigenvector helps us to find the combining factor for the first canonical variable. What about the second canonical variable? To do that, what we observe is that, interestingly, this lambda 1, lambda 2, lambda r in that order comes out to be also the r largest eigenvalues of the matrix sigma 2 2 to the power minus half, sigma 2 1, sigma 1 1 to the power minus 1, sigma 1 2, sigma 2 2 to the power of minus half. This matrix, however, is of dimension S, and S is greater than R. So, S has more eigenvalues than R. It has S eigenvalues, but the largest of this eigenvalues, the largest R of this eigenvalues would be the lambda 1, lambda 2, lambda r we have obtained already. That can be mathematically shown. and corresponding to this lambdas, we get the eigenvectors from this matrix as q1, q2, qr. So, when I combine V1 with q1, this q1 actually is the eigenvector corresponding to the eigenvalue lambda 1, but coming from the second matrix that we have just defined. So, this way we can get the first canonical variables and the first canonical correlation. In general, the kth pair of canonical variables will be given by uk, which is pk prime sigma 1 1 to the power minus half x1, and vk equal to qk prime sigma 2 2 to the power minus half x2. And this would give us the correlation between uk and vk as square root of lambda k. So, this correlation obviously would be smaller as we go, as k increases. The first one would have the maximum correlation, the second one would have a slightly less, it will be the square root of lambda 2, etc., and this would be decreasing as k increases, and we can go up to r for this. So, this is how we can find the canonical variables and the canonical correlations. Usually, we only work with the first, second or the third canonical correlation and the canonical variables and discard the others because they have less information. Typically, it is the first canonical correlations that we are usually interested in, as we will see later on. But very quickly, let us look at some of the properties we have of the canonical variants. The variance of uk and the variance of vk would both turn out to be equal to 1, and we can expect that the covariance between uk and ul would be equal to 0 for any k not equal to l. So, if I look at the first set, and from the first set if I get r canonical variables, so the first canonical variable, the second canonical variable, etc. for the first set, all these are uncorrelated among themselves. Similarly, the canonical variables from the second set are uncorrelated among themselves, that is, covariance between Vk and Vl is going to be equal to 0 if k is not equal to L. Further, any canonical variable from the first set and a canonical variable from the second set, if they are not of the same order, they would have a correlation of 0. That means, if k is not equal to L, then covariance between uk and Vl is going to be 0. So, only when uk and vk have the same order, you have a correlation which is the canonical correlation of kth order, which is given by square root of lambda k. This result can be proved using a certain matrix algebra techniques, which are not very difficult, but will not be doing the proof here. Instead, let us look at some of the other results. In today's lecture, we had been looking at canonical correlation analysis, which basically helps us to find the correlation between two sets of variables. Usually, when you have two sets of variables, one comprising of r variables and the other having s variables, there will be r into s correlations. What the canonical correlations actually do is to summarize this into 1, 2, maybe 3 or 4 canonical correlation coefficients, which helps us to get a good understanding of the correlation between the two sets in a very few number of values. That is what we do, and what we will do in the next session is that we will be looking at the properties related to this canonical correlation coefficients.